Hi everyone, I'm Mr. Fullerton, and today I want to talk to you about free body diagrams. Free body diagrams are a tool that show all the forces acting on an object and allows you to more easily analyze a physical situation. We'll also talk a little bit about pseudo-free body diagrams. If you make a free body diagram and all your forces don't line up with an axis, sometimes if you take one more step and break those forces up into components in what's called a pseudo-free body diagram, you can make your life a whole lot easier. So let's take a look at these. To begin with, a free body diagram shows all of the forces that are acting on a single object. The object itself may be drawn as a dot, so you don't need any amazing artwork skills in order to make these diagrams. Further, you start off by choosing the object of interest, drawing it as a dot, and then you're going to draw and label all of the external forces acting on that object. Then sketch a coordinate system, typically choosing the direction of the object's motion as one of the positive axes, and then you're all set to go do your analysis. Let's take an example. Here we have an elephant walking on a tightrope, and apparently our elephant had a bad day and fell off the tightrope. As he's falling, let's draw the free body diagram for our elephant, and we'll neglect air resistance for this problem. Well, to draw our elephant, we start off with a dot. There's our elephant. And what forces act on the elephant as he's falling? Well, of course, we must have the force of gravity on the elephant, and gravity is going to pull the elephant down. And we could write that in several different ways. We could write that as Fg is force of gravity. You'll see some folks write it as capital W for weight, or maybe force of weight. Any of those are acceptable, but my favorite, because I think it really saves you time in the long run, is let's get rid of those and let's write it as mg. The mass of the elephant times the gravitational field strength. If you always write the force of gravity as mg, you'll get away from some later complications and worries about things like, does W stand for weight or work or watts, other things like that. Mg used as the force of gravity on an object. That's the only force acting on our elephant. There's our free body diagram. If we wanted to sketch our axes, we could have our x and y axes, and we're done. Let's take another example. Our poor elephant again falls off the tightrope, but now we're going to include air resistance while the elephant's in the air. Once again, our elephant is a dot. We have the force of gravity, mg, acting on our elephant, down of course, and air resistance is a type of friction. It opposes the motion of an object. So as the elephant is falling down, air resistance must point up. It's actually going to slow the elephant down. So we'll draw another arrow, another vector, and label it FA for air resistance. That easy. Here's another one. We've got a glass of soda sitting on the table. What forces act on the glass of soda? Well, we'll start off by drawing our glass of soda. There's our dot. We have the force of gravity, mg, acting down on our glass of soda. But why doesn't it just go through the table? Well, there must be some other force acting upward that is balancing that force of gravity. We call this the normal force, or capital F sub n. And in some books, you'll see it actually written as just capital N. Doesn't really make a difference. What the normal force is it's a force from the table. As the glass is pushing down on the table bends just a little bit, and it has almost like a spring is pushing back up to balance that. And they call it normal, not because it's not weird or not strange, but normal is a geometry term meaning 90 degrees. Sits this way. The normal to the table must be perpendicular to the surface or up out of the table. That's what they mean by normal. It's always perpendicular or 90 degrees to the surface the object is sitting on. So our free body diagram for our glass of soda sitting on a table. Let's see if we can't apply this to a couple problems. Although these aren't specifically free body diagrams, I think you'll get the idea. Which diagram represents a box in equilibrium? An equilibrium means there is no net force on an object, or all the forces on that object are balanced. Well, if we look for the diagram where everything's balanced, it can't be number one, because we have 5 down but nothing up. It can't be number 2 because we have 2 up and 5 down. That's not balanced. Number 3, we've got 2 up, 2 down, 5 right, and 5 left. That's got to be balanced. 2 newtons up, 2 newtons down gives you a net force of 0 newtons in the vertical direction. 5 newtons right, 5 newtons left gives you a net force of 0 in the horizontal direction. Correct answer must be